Hey everybody, this is Mr. Piercy, and what I'm going to be demonstrating in this video is what happens when I have congruent chords in a circle and their relationship to the center of the circle. So for the investigation that we're going to do for the demonstration, if you're trying to follow along, I'm going to use a compass, a straight edge, and a pencil to demonstrate this particular property of chords. So I'm going to begin by creating a circle on a piece of paper, and we have something like so, and inside of the circle, and let's call this circle C just to give it something, some kind of a name. I'm going to create two congruent chords inside of the circle. Now here I will kind of pick a random point here and a random point here, and I'm going to construct two chords from those points. So we'll call this point J and K here, and you can open up your compass to be whatever you want it to be, just as long as it works for the circle itself. So like you can see here, the way I have it open, I'm not going to be able to actually make a chord, so I'm going to close it up a bit, and I will kind of somewhere about here, and I'm going to create another arc that intersects my circle here, and then from point K I will recreate the arc somewhere else, and we'll name those points L and M. So taking my straight edge, I will make the chords of the circle that we're going to be working with. So here's J, L, and here's KM. Okay. Now specifically what we're looking at here is what is the relationship between these two chords that are congruent to each other. So we've constructed JL to be congruent to KM, and we want to know what is the distance from the center of the circle. Is it the same or is it different? Now there's a theorem, maybe just a postulate in geometry. I know the postulate in geometry says the shortest distance between any two points is a straight line. Well, the extension of that is the shortest distance between any two objects is going to be along a line that is perpendicular to the two objects. So if I was standing here at point C and I was going to walk to segment KM or to segment JL, if I was going to walk to those, the shortest distance to go from one point to the other would be along a line that would be perpendicular to those segments. You know, just imagine when you're going to the grocery store or something, and you're in your car trying to drive along the path in between the parking lot and the grocery store, and you see the people that are kind of walking diagonally across the road, and you say, well, it's taking forever, just go straight across. That's because the shortest distance between where the cars are parked and the front of the building would be a perpendicular line between the two objects. So what I'm going to do here is I have to create a line that's perpendicular to my segment here and goes to this point. So what I'm going to do is I'm really going to kind of just cheat. I'm going to line this. It might be a little hard to see. Let me zoom in just a bit for the moment here. What I'm going to do is I'm just kind of going to line up the little tick marks here, the little hash marks on my ruler, so that way it's sitting right on top of my segment, and I will line that up with point C and then draw in my segment. Now, my ruler, my protractor is a little too short to see this. I'm not sure if it'll necessarily, you can really see it that long, but you can kind of tell if we extended the line out far enough, we would see, get my fingers out of the way, that it would be right at 90 degrees. So there's that segment, and we'll call this point right here, we'll call this point A. And then I'm going to repeat the process from the other chord. So again, I'm going to just kind of take my little horizontal lines or my little hash marks here for my measurements on the ruler, and I'm going to line it up with the segment that I'm trying to draw the perpendicular line from. So I'll come here and from point C line up. You see how the horizontal or the tick mark for 3 is sitting right on top of the segment. Now that lets me know if I draw in that segment there that it also should be perpendicular. And just take a quick moment, just kind of gauge it, and you can kind of see if you take another straight edge there, you see it goes pretty straight towards 90 degrees. So this segment here, CA, and I'll call this point here point B, those two segments are now the same length. Well, I'm getting ahead of myself. Those two segments are perpendicular to each other, but I kind of gave it away. If I look at the distance from C to B, from the center of the circle to the chord, and I look at it from here, from the center of the circle to the chord, we can see that those are the same length. And that allows me to conclude that if I have congruent chords inside of the circle, let's go ahead and write this down. If two chords in a circle are congruent to each other, like JL and KM are, then they'll be the same distance or equidistant. From the center of the circle. And we could easily take the converse of that statement also. So what I mean is that if I started off by saying that segment CB and segment CA were congruent to each other, then that would allow me to, especially if we're told that they're perpendicular to the chords, then that would allow me to conclude that the chords of the circle would be congruent to each other also. So that's it for this particular lesson. Again, just to recap, if I have congruent chords inside of a circle, they will be the same distance away from the center of the circle.